say find where the function is discontinuous and classify the discontinuity as removable, a jump, or due to a vertical asymptote. Take a look there at number 1. Oh, there it is. So number 1 says g of x is equal to x squared minus 1 over x minus 1. There we go. Okay, so gosh, I don't know. Let's not use like a graphing calculator for this. We can kind of consider what the graph looks like, but let's kind of work with this right here. It does kind of imply, the wording implies that it is discontinuous somewhere. Where would you say, just kind of based on a quick glance, where would you say that it is discontinuous? X equals 1. Why do you pick out x equals 1? Several of you said that. Okay, so there's a gap. Josiah said you can factor stuff out and cancel. Yep, I agree. So let's do that. If we did factor and cancel, we'd get g of x is equal to x plus 1 times x minus 1 over x minus 1. Those would cancel. And I think it's pretty universally true if you're ever able to cancel out factors like that, the resulting graph will just have a hole right there at that factor of x minus 1, therefore it would be x equals 1. And so to answer the original question, where's the function discontinuous? We would say discontinuous at x is equal to 1. Bless you. And Josiah said gap. And somebody else said hole. I said hole. I don't see that as an option. It says removable, jump, or vertical asymptote. It's removable, yeah. So we talked a little bit about this, I think, over the summer somewhat. Can anybody explain, do you think you know, why would that be called a removable discontinuity? What do you think, Ben? Yeah. Yeah, you could drop a piece right in there and it'd be continuous. Yeah, exactly right. So neither of the other two, the vertical asymptote or the jump, those are not removable. There's nothing you can do about those. But the little hole in the graph, you can certainly remove that discontinuity by plugging up the hole with some sort of piecewise graph. All right, do you have any questions? Okay, so if we were going to use the notation we looked at in the video, we could say something like this. We could say the limit as x approaches 1 of g of x does not equal g of 1. So can you tell me if we did try the discontinuity statement with the limits and everything, if I did calculate the limit as x approaches 1 of g of x, what would the answer be? 2, right? Because couldn't you just plug the 1 into the canceled out function? Yeah, so sorry, that should have been not equal to. So you'd say 2, sorry, I left off the little slash. 2 is not equal to, what's g of 1? That's dne, isn't it? Yeah, so the value of the function doesn't exist, but the limit is 2, meaning that it's not continuous. Okay, so number 2 is kind of like number 1. Will you guys try that on your own? Feel free to discuss, use limits and function values and whatever, come to a conclusion, come to a value, and see if you can use good notation in expressing any discontinuities you might find. You guys all had a chance to work through number 2? You're all okay discussing this? You guys have been discussing a little bit. It's definitely okay to talk about these things. There is a discontinuity. What kind of discontinuity is it? Peyton? It's a jump, yes. So the two pieces there, like the way to maybe illustrate the jump, did you use limits?
Yeah.
I think you definitely want to do that. What limit did you set up?
So I set up the limit for as x approaches 0 from the positive side for h of x equals 0, and then limit.
I don't think that equals 0.
Oh, negative 1, sorry.
From the, well, we're getting a little picky here. You said from the right?
Yeah.
So from the right, I would say that would be 1. There we go. Equals 1. Okay, keep going.
Okay, and then limit as x approaches 0 from the left or negative for h of x, that would be negative 1.
Yeah. So as you approach 0 from the right, you get 1. As you approach 0 from the left, you get negative 1.
Yeah.
And all we really have to do at this point is say, those are not equal to each other, right?
Yeah.
Fill in that little gap right there. Those are not equal to each other. So since the left-hand behavior and the right-hand behavior are different,
It has to be discontinuous.
yep. Therefore, I'll put it like this. Therefore, H has a jump at x equals 0. Therefore, H has a jump at x equals 0. Okay, you guys come to the same conclusion. Do you have any questions? Jake, go ahead.
Would you say that's removable or is that
Non-removable. Non-removable. If we looked at a graph of this, let's see here. We'll sketch it out best we can. So to the left of 0, it's 4x minus 1. So something like that. And to the right of 0, it's the parabola x squared plus 1. So the graph looks something like that. So there's a couple ways to look at the whole removable versus non-removable. You can think of it categorically. So if you simply have a hole and that's it, then it's removable. Anything else is non-removable. You could also think about the graph though. Think it through like this. Is there any way I could add a piece to this graph, like go one more piece or 2 or 3 more pieces or whatever I need and fill in the discontinuous part? I don't think there is, right? It would cease to be a function at that point. I mean, you could put in a vertical line, except you really can't because it's y equals and a vertical line is x equals. So I just don't think there's a way to do it. Same thing with a vertical asymptote. Good question. Did I clear that up for you?
Yeah.
Okay, good deal. Anybody else? Please don't be shy. I'm here to serve. I'm here to help. If you ever have one of those what if questions, like what if the function looked like that? What do you think,
So
Riley?
what if like the first function was 4x plus 1? Would that still be discontinuous?
Well, let's change that and let's analyze. That's a good what if question. So guys, this is a totally different question, right? This would be a totally separate question, but it's a good one. So if the original was really 4x plus 1, oops, instead of 4x minus 1, how would that change things? Well, when you look at the limit from the right, we still get 1 because that hasn't changed. But the limit from the left would not be negative 1 anymore. What would it be? It would be 1. So it would actually end up being a continuous function. There would no longer be a jump. What that would effectively do is that would, if you remember before, it was the line did this and the parabola did that. By changing that to 4x plus 1 instead of 4x minus 1, that would take that little linear piece that was down below and actually move it up there. So it would be a continuous function. No longer would there be any discontinuities at all. And it's funny you would ask that because we're actually going to work on that same situation here in just a few minutes. What if questions are pretty much always good. Unless it's what if I'm lazy? And it's like, stop. Okay, great question. Anybody else? Fantastic. Okay, so number 3 will be a good challenge for you. Number 3 is certainly not an uncommon question that this sort of question that I would ask or you'd find on an AP test. Very conceptual. If you think about a question like number 3, it's all about notation and understanding concepts. There's like almost no arithmetic to be done, is there? I don't really think there is any. So let's read it here together, and I want you guys to discuss and talk this one over. You do have a 33% chance of getting this right if you just guess, but I would like for you to discuss to the point where you feel like you got a better chance than that. So it says, if f of x is not continuous at x equals 2, which of the following must be true? Must is a very strong word. That means that it has to be this, right? There's no other way. It's got to be specifically this choice. So the word must is important. If the word must was like could, then it would radically change how you would approach this, right? If the word must is in there, so we got to think of it in terms of that. You got your options there, so please discuss, come to a good conclusion, and we will later discuss. Hopefully get a good answer. What I'd like to do is discuss these options in terms of what the graphs would look like and the types of discontinuity. So the word must is in there, like I said before. It's very important. Which of the following must be true? Oh, it's frozen. Thank you. So take a look at A, though. Take a look at A. If, there we go. So if we look at A in terms of what type of discontinuity it would be, it's a jump, right? Because we're saying essentially the left-hand behavior and the right-hand behavior are different, right? They don't equal each other. And so A is basically expressing a jump. Let's take a look at B as well. So B says f of x is not defined at x equals 2. What are the possibilities there for what the type of discontinuity your graph might look like, Zach?
A removable or gap discontinuity or vertical asymptote.
Yeah, it could be removable. Oops. Or it could be a vertical asymptote. We're not really sure totally what that would be, but it's kind of describing one or the other. So I am here to tell you that C is the correct answer. And can I explain why? If you have a discontinuity, think this through. If you do have a discontinuity as expressed here, and A is the answer, doesn't that mean that if you have a discontinuity, it must be a jump? See what I'm saying? Like, if you have a discontinuity, it doesn't have to be a jump, does it? If you put A, you're telling me that all discontinuities are jumps. Does that make sense? Aren't there other types of discontinuities? Just because you have discontinuity doesn't mean that it's a jump. B is a little closer, isn't it? Because isn't B saying, hey, if you have a discontinuity, it could either be a hole, the removable thing, or vertical asymptote? That's closer, right? But B is ignoring the possibility that you might have a jump. C is really the only one that incorporates all three possibilities of discontinuity types. So in C, the f of 2 is not equal to the limit as x approaches 2 because there's a couple reasons for this. Like, let's say that f of 2 is defined. You could have these would all have to do with C. You could have this. You could have f of 2 being defined, but you might have a jump. Like, that's what that's describing right there. You could have the limit exist. Maybe the limit is, I don't know, maybe the limit is like 5, and f of 2 is dne. That would be defining a hole or really a vertical asymptote. Only C really incorporates all the possibilities. If we looked at a graph, of course, let's look at it like this. This might be a better way. So you could have a jump. So in a jump, f of 2 is defined perhaps, but the limit doesn't exist. That fits with C, doesn't it? With a vertical asymptote, right there, well, f of 2 doesn't exist, and neither does the limit. You might say, hey, does dne equal dne? No, it doesn't mean that it's continuous, right? It simply does not exist right there. And then, of course, you could have the removable discontinuity. This would be where you could certainly say the limit exists, but the value of the function at that 2, I guess, would not exist. So only C really incorporates all three possible types of discontinuities, so you really have to go with C. All right, so do you guys have any questions? It's a good one, right? That's a good question. It makes you think, discuss a little bit. Tests and quizzes are not filled with those, but you can count on questions like that being there at times for sure. Okay, so you guys have done a really nice job working through a couple of examples on your own as groups, but I want to do number 4 with you. So if you would, turn to number 4. This is one I want to make sure that I communicate as clearly as possible what's expected. So you guys notice a couple things about this. Number 1, it is open response or free response, right? There's no multiple choice or anything, so that really implies you've got to show your work. You've got to communicate clearly what you're doing. And it gives you this piecewise function, g of x equals all that stuff. It says find the value of a so that g of x is continuous for all x. And this kind of goes to Riley's question earlier, her what if. Like, what if that -1 was a 1? How would that affect things? Didn't her question lead us to basically taking something that was discontinuous and transforming it into something that is continuous? That's kind of what this is about here too. It's saying, hey, let's figure out what a would have to be so that we have a continuous function for g of x for all x. So let's go through some assumptions here for a second. what kind of a function is the top piece? And cubics, just think about what a graph of a cubic looks like. Isn't it always continuous? It's a nice, smooth, continuous curve. They're always continuous. And so the top piece is continuous. What kind of a thing is the bottom piece? It's a line. So again, same thing. Lines are always continuous. And so what is the only possible spot where we might have a discontinuity? -2, where these two functions maybe join or don't, right? And so we want to make sure that we have a continuous function for all x, so we're going to focus only on -2. So I want to give you guys a hint about this. If you are ever asked about continuity, if you're ever asked things like this question where it says find a to make this function continuous, or prove that this function is not continuous, or prove that this function is continuous, if you're ever asked a free response question about continuity, you want to start in one place only, and that is that limit statement that you saw in the video. Okay, so I'm going to show you what I would expect here. I would write something like this. Limit as x approaches -2 from the left of g of x has to equal the limit as x approaches -2 from the right of g of x, and that has to equal, both of those have to equal g of -2. So that's that statement you want to start off with whenever you're asked about continuity in a free response setting. You could even do it in a multiple choice setting if you wanted to, but for sure with a free response, you've got to do that. Okay, place to start. You remember that from the video? Hope you do. Go back over it, review it as needed. Let's go ahead and start filling some things out. So what is the piece that's from the left? Is it the cubic or the line? The line has the less than -2, so that is the left piece. So I'm going to go ahead and use that direct substitution that we've practiced. So -2 just gets to go right in there for x in the line. So let's see here, that would be -3/4 times -2 minus 2. Supposed to equal the limit as we approach -2 from the right. Of course, that must be the cubic. So same thing, I'm just going to plug the -2 in for x. So it's going to be a times -2 cubed plus 4. And which of those two pieces actually contains g of -2? Yeah, the cubic does. And so I'm just going to go ahead and put g of -2 right there. I don't need to rewrite the cubic. I get it. And then beyond this step, I think I'm just going to leave that g of -2 off because I realize that that's incorporated in the cubic. Make sense? Any questions so far? From here on out, it's going to be some pretty generic algebra. This has kind of been the calculus part. Okay, so we do some arithmetic there. 3/2 minus 2. Did you guys get -1/2 right there? And that is equal to -8a plus 4. So maybe we subtract 4 from both sides. So -9 over 2 equals -8a. And then drawing on all those Algebra 1 questions you did, we divide both sides by -8, and we're there. So you guys get 9/16. So 9/16 is equal to a. Pretty amazing, right? This is certainly not one of those things you could probably guess at. Hey, what does a need to be to make this continuous? You're like, I don't know, 5? No. How about 9/16? You're not going to just like pull that out of a hat, right? You're definitely going to need to show these steps, and if you do, I think you should be in pretty good shape. So, can we pretend this was a quiz question, and I was going to assign points to this? Yeah? Okay, I'll do it anyways. So let's say this was a quiz question. I would definitely give this original limit statement. That would be a point. So it'd be entirely possible for you to get 9/16 and not get full credit because I need to see that you started off with limits. Okay? So I'd say that first statement is definitely worth a point. And then this point right here, I would definitely give you one more point right here for basically keeping the left and the right stuff straight. You know, like you're showing evidence that you get all the left and the right associated correctly. And then the whole rest of this stuff right here would just be worth 1 point. Basically, essentially getting to the right answer would be worth 1 point. What I'm trying to do there is place emphasis on the points that are associated with kind of the calculus of it. And the algebra, we all make mistakes on algebra, but that's not the thing, so I'm not going to give you like a point for all these little steps with algebra. It'd be more about, do you understand this concept, do you understand what this means, and did you get the answer? So maybe a 3-point question, something like that. That make sense? Okay, fair enough. So I wanted to do that one together. If you want to do one of those on your own, if you're thinking about preparing for your quiz, that would not be a bad idea at all. And I think you'll find at least one of those in your extra practice, and I think you'll find some of those in your WebAssign too. Okay, so I think at this point you could do number 5. Number 5 is a little different because it's different from 4 because there's no a value for you to find. This already has this function set up, but it wants you to show that h of x is continuous for all x. Show that, what's that another way of saying something else? What am I really trying to get you to do? Prove, right? Show that really means prove that this is continuous. It's open response, so you'd want to start off with limits, right? So give it a shot. We'll check your answer in a second. So again, I want to give you a good example of what I would expect here. I don't want there to be a mystery. If you're asked to prove continuity or prove discontinuity or find continuity or something like that on an open response, you want to always start off with limits. And so we'd go limit as x approaches 4 from the left of h of x. Needs to equal, the limit as x approaches 4 from the right of h of x, and then both of those have to equal h of 4. That's where we want to start off with. If we can prove that statement to be true or false, we can immediately draw a conclusion and we're done. But you would need to use limits. Like, I'll be as clear as I can. Like, LIM needs to be on your paper. That make sense? No, I just plugged it in my head. It's like, I get it. I totally get it. But LIM, remember, as we talked about, LIM carries a very different meaning than just plugging the number in. Right? You're telling us, you're communicating a little different thing. Okay, so as you approach 4 from the left, that would be the line. And so, let's see here, half of 4 is 2, minus 48 is negative 46. And hopefully that equals 4 from the right, so that would be the parabola. So it's 16 times negative 3 is negative 48 plus 2. Looky there is negative 46. Which piece actually contains h of 4? Bottom piece, and we already know that that's negative 46. And so since all three of those numbers are equal to each other, we can say, therefore, h of x is continuous for all x. We're making an assumption when we say that, because haven't we only proven continuity at 4?
Yes.
Why can I extend that to say for all x? Why, Catherine?
Because the top one is a square function which would be continuous.
Yep.
But the only point, and the bottom was a straight line, so the only point it could be discontinuous is because it's a piecewise function.
Yep, exactly. So we're looking at that joining point, and we did, so we're good with all of them at that point. Well said. Okay, any questions?
Is
Matt?
that last part assumed, or should you write out that the two functions in piecewise aren't discontinuous?
So we would probably assume that, right? Because if you were going to go through and try to prove that the top piece was continuous for all x, you'd never finish, right? You'd be like, all right, today I'm going to do all the numbers between 1 and 2, except you'd never finish that even, right? So yeah, so we kind of have to assume that we understand, and we're going to get into that right here in a second, like why we're all comfortable assuming that, but then you definitely just want to do that. Yeah, good question. Because it does seem like a pretty big assumption, right? We only dealt with 1 point, how can we say all of them? So yeah. Okay, good question. Anybody else? All right, here we go. Let's finish this up. So classic functions and their continuity. So we've hinted at this for sure. Polynomials, those are our friends, right? Polynomials are super nice. They are always continuous. Examples of polynomials would be lines, quadratics, cubics, quartics, 5th degree, 6th degree, on down the list. Those are all polynomials, and all polynomials are always continuous for all x. So it's kind of nice when you see a polynomial, you could just jump right there. Okay, the next one is rational. What does rational really mean? Ratio, meaning it's a fraction, yeah. So if you've got a rational function, an example of that would be something like, 1 over x, or x cubed plus 2 over x squared minus 1, things like that. We might have some issues with those, right? Peyton, what do you think?
So if there were a state in the law that polynomials are always continuous?
Yeah, I don't think I would ever give you a polynomial and say, is it continuous for all x? For the same reason I mentioned with Matt, like you'd never finish the question, right? Because you'd have an infinite number of numbers to test. But if I do say, yeah, hey, a function is a polynomial, you want to mention it. You actually want to say, well, hey, it's a polynomial, so it's continuous, and therefore I can do these things with it. Remember, like we talked about the IVT, the condition for the IVT is that the function has to be continuous on the interval. If I tell you it's polynomial, you can be like, hey, it's a polynomial, so it's continuous, therefore I can do this stuff.
Okay.
Yeah. Okay, so what kind of discontinuities might show up on rationals? Asymptotes and holes, right? So you could have all of the above, so you'd want to be careful with those. I'll put asymptotes and removables. Radical functions, like square root functions, what's kind of the main issue with square root? Like what can't you do with a square root? Yeah, negative input, right? So you can't do square roots of negatives. So I'll just do that. So if you are potentially going to be doing a square root of a negative, you're probably going to have a large area that's not continuous, right? The function simply just won't exist in certain areas. And there's a variety of ways that could look. Trig functions, this is kind of a mixed bag. Like there's going to be a variety of things that could happen here. Which trig functions are always continuous? Sine and cosine. Yep, so sine and cosine, always continuous. And what do the rest of them have? They all have asymptotes. So there's secant, cosecant, bless you, tangent, cotangent, all have vertical asymptotes. And so those would all be things you'd want to look out for. The purpose of this list is just to kind of remind you of kind of the general patterns of functions and which ones are going to be easy to deal with, which ones are going to be a little harder to deal with. You know, just a reminder. Hopefully it's not something that is that new to you. Let's see here. So we've got a couple of IVT questions left. I think what we'll do is we will revisit those because I think our class is over in about 2 minutes, right? Yeah. Isn't it 25? Yeah. I think we'll revisit those next time. I want to mention a